Hello and welcome to a quick introduction to MixIT on the web. If you're a first-time user, you can go on to the sign up page and sign up with your credentials and get access to MixIT. And if you have already registered and have access, you can go onto the sign in page and sign in with your credentials. And once you sign in, you get this view where we have a couple of modules. And the first module is the database module. The database module is a Reactor Navigator system where you can create your own geometries and your own processes with different process conditions. And let's go through an exercise to get a feel of it. So let's go and create a new reactor, let's say named A4, and then configuration name C4 and process name P4. And let's say it's site 1 and the scale is lab scale equipment. So once we have created the initial reactor, we can go on to the configuration and customize the geometry as per our needs. So we offer two types of tank shapes, which is cylindrical and rectangular, and we give the option of changing the diameter and the height. We have a few the styles of the head and the bottom, which are conical, elliptical, flat, hemispherical, and toruspherical. And we give the option of having no baffles, or standard baffles, or even custom baffles if we wish to. You can even have multiple impellers, which can be set over here in this view, and as we can see, they have a few distance between them with this clearance value. So let's save this and then go on to the internals, where we can put in jackets, or if we have any helical coil, we have any ring spudger or tip tubes, so we can even add those. So once you have created your own geometry, and for shaft design you can give in the appropriate details. So once that is done, we go on to the process and then put in our process conditions, which are basically liquid volume, fluid properties like density, viscosity, even able to choose what kind of fluid type it is, Newtonian or non-Newtonian as per the rheology of the liquid. And then we can choose the impeller speeds, whether both the impellers should run on the same shaft or same speed, or if they're offset, we can even give different conditions for the speeds. So let's go through some of the different kinds of reactors we can make. So here we have a radial flow impeller with a few dip tubes and a ring spudger and a helical coil. And then here in this, we can see there are multiple impellers with two on the same shaft, and one is at an angle. So we can see that we can have different geometries at different orientations as well. So the next module is the CFD analysis module, where which you can use to have a fully automated CFD process. And so let's go ahead and create one. So let's say the name of the process is job CFD, and then we choose an appropriate process. So let's select the P4 that we just chose, and then here we can choose which server to run it on. So you can choose either MixIT Cloud or your own server or Linux machine if you have one, and then you can choose the number of processes to run the CFD on. You can even you can choose the mesh density or the mesh quality that you want to run the CFD on, the type of turbulence model for computation. If it's laminar flow regime, then you choose the laminar, or if it's turbulence, then you can choose one of these available models. You can even choose a number of iterations for different kinds of discretization scheme that you have for your first order and second order iteration. So let's give 100 and 400, and you can even solve a heat transfer if you wish to, and you can even solve for mixing of a blob of fluid, how it will mix through the bioreactor. So let's give a small amount of blob of fluid and see how it mixes. So okay, it's colliding with the coil, so let's change it a bit. Alright, so we have our blob of fluid, and we can change it a little more. Okay, and then we can give the time step size, the number of time steps, and how much to save the data after how many time steps. So let's go ahead and solve this. And if we want to solve a gas enabled system as well, or solids loading, then we can do so also. So once we have put in the conditions we want, we solve this. And while this is running, I'll go through a already solved case, and here we can see what all cases are running and what all jobs have been completed. So let's go through one of the completed jobs. So here when I click on this, we can see the details that we had given for the simulation, and then here is the status log of that simulation from the time it started at the time it completed. And then here we have the results view. So in the results view, we have a few different kinds of results. So first is the performance parameters, which are the numerical results that are the output of a CFD simulation, and these are typically parameters or metrics that we call them, which are used to understand a process. And we have them divided in two groups. So the first group is the whole bioreactor group, where we get a whole volume average metrics like the power per unit volume, or the volume average strain rate, volume average velocity, etc. And then we have the impeller specific parameters, which are like tip speed and power number and flow number. And if we have multiple impellers, we'll get multiple sets of those values. And then we have the flow profiles tab, where we get some contours at different planes, like the velocity contours and velocity vectors, basically describing the flow profile of the flow inside the bioreactor. And we even have shear distribution to understand how the shear is distributed in the bioreactor with the help of these contours and the histogram. And here on the right side, we have this download drop down, where you can download this as a Word document, or even the results folder, which is basically a combination of all these, or even the whole entire data set of your simulation. So let's download the report doc and see how it looks like. So once we have this report doc, it's a collated report of all these velocity contours and shear contours, and the metrics in a tabulated form. Thank you.